Practice problem number 4, associated with sample problem D. If the pelican in item 3, right, so that was practice problem number 3, okay, the previous video, if that pelican was traveling at the same speed, and just so you don't have to go watch that entire video again, I'll let you know that we figured out that its velocity in the x direction was 7.6 meters per second. Okay, so same speed. Okay, so you have to go look at the previous practice problem if you don't believe me, but that is the same speed. But was only 2.7 meters above the water. How far would the fish travel horizontally before hitting the water below? Now again, in the previous problem, the pelican was traveling at 5.4 meters above the water. So in this version, in practice problem number 4, the pelican's only going to be 2.7 meters above the water. But let's give it a shot. So we know that delta y is 2.7 meters, but again, the fish has to fall, right? So again, remember our coordinate system, plus, plus, minus, minus. That has to fall. So my delta y is going to be negative 2.7 meters. We're still working with good old-fashioned gravity, so that acceleration in the y direction is going to be equal to the force of gravity. But again, it operates in the downward direction, so we need a negative sign. So negative 8.1 meters per second squared. Now, in the previous problem, actually in all the practice problems for this particular sample problem, we've been using the kinematic equation that allows us to create substitution representations of time. Which would be very, very useful to solve here. But we're going to tweak it just a little bit. Now, this time we're actually being asked to solve for this delta x. Now, there's 0 acceleration in the x direction, in the horizontal direction. That means that the numerical value for acceleration is 0, which allows us to get rid of that entire side of the equation. And so I actually have an expression that solves for exactly what I want. Delta x, right? The displacement in the horizontal direction, right? How far would the fish travel horizontally? But here's the thing. I don't have a value for delta t. Now I have a value for this initial velocity, right, the 7.6 meters per second, but I do not have a value for the delta t. I'm going to use kind of the same, I guess you could call it a trick, and there's not quite a trick, to get a value that I can substitute for this delta t, right? So this bad right there is the issue. Okay, that's the issue. But if I recognize that there's 0 initial velocity in the y direction, that means that the value of this velocity is 0. So it doesn't actually matter what this time interval is. It's being multiplied by 0, so it's going to go away. And I have a value that looks like this. But here's the thing. I want to solve for delta t. So that means I need to get delta t all by itself. So in order to do that, I'll multiply both sides by 2. That'll allow me to cancel out that 1/2. And I'm going to divide both sides by a. That's going to allow me to cancel out that a. Don't forget that that delta t is squared right there. So I'm going to have to square root both sides to get rid of that square. So I end up finally solving for delta t, and it looks like 2 delta y divided by acceleration, all square rooted. This is super useful because this is going to allow me to take this expression, which has 2 variables that we do have values for. We have a delta y and we have an acceleration. So I can actually represent delta t numerically and then plug it in for this value. All right, I'm going to take this, go up there. All right. Okay, so let's represent. So we have a delta x is equal to that initial velocity, and that's going to be multiplied by our delta t, which is the square root of 2 delta y divided by acceleration, which ends up being 7.6 meters a second. And then I have to do my big radical. So that's going to be 2 multiplied, let's see, that's negative 2.7 meters, all divided by negative 9.81 meters per second squared. Okay. Now this ends up being, fairly easy to do in the calculator, so I don't rearrange anything. Okay, like I did in the previous practice problems. Looking at the question, I only have 2 sig figs in the values that I'm using here, right? 2.7 from the actual question, 7.6 from the previous practice problem, right? Practice problem number 3. So my answer is going to have 2 significant figures, and it looks like I'll keep that at 5.6 meters. Okay, you'll notice that the relationship between the fact that the fish didn't fall quite as far in practice problem number 4, right? Only 2.7 meters as compared to 5.4 meters in practice problem number 3. So it didn't fall nearly as far, right, in the y direction. It wasn't in the air as long, so naturally it didn't actually move as far horizontally, right? Just 5.6 meters compared to the 8.0 meters from the previous practice problem.